I will begin with a word of prayer. Dear Father, we thank you for this day, and I thank you for this class. Just ask you to guide our steps today. Help us to just understand more about principal ideal domains and Euclidean domains and all these things, Lord. In your name I pray, Lord Jesus. Amen. All right, so we have introduced a fair number of definitions and terms, and we will touch on those again as we do proofs today, so that's good. This is lecture 10, which is ostensibly on principal ideal domains, but we've been talking about principal ideal domains for a few days now. So there you go. And so a nice abbreviation for that, of course, is PIDs. And so like last time, we introduced norms on rings and Euclidean domains, and we also defined associates, irreducible, and prime elements. And so this material is roughly my old lectures 27 and 28, which largely corresponds to like Dummett and Foote sections 8.1, 8.2, even 8.3. But today we should probably work more with primes and irreducible elements, I'm hoping, and I'll give you some examples. Now, I should remind you guys, last time we proved theorem 4.78, which simply stated that in an integral domain, all right, that's our context, if A is prime, let me say X. If X is prime, then X is irreducible. And what did that mean? What did it mean to be irreducible? It meant we couldn't factor it, or if we did factor it, at least one of the factors was a unit. All right, so I would say there's no non-trivial factorization of it as a way you could characterize irreducibility. All right, and then also, if we have R a commutative ring with 1, if A and B are associates, right, which means that we can find a unit and B is equal to AU for some unit, right? That means they're associates. Then the principal ideal generated by A is equal to the principal ideal generated by B. And furthermore, if R is integral domain, right, and we have some ideal which is generated by A, and that same ideal is generated by B, then what can we say about A and B? Fill in the blank for me. No solutions. What does that mean? No. What? I mean, you have associates. Very good. Oh, I thought you said no solutions. I guess I'm. My bad. All right. So associates. Thank you. Cool. Now, what if R is not an integral domain? Could this still happen? Does it have to happen? Can this theorem be strengthened? Does it? I mean, what's the deal? So, an example, our example 1 for today, is you could look at R equal to Z6, right? And if we look at the ideal generated by 2, it's the same as the ideal generated by 4, which is namely 0, 2, and 4, right? Are 2 and 4 associates in Z6? Well, how about this? 2 times 5 is equal to 10, which is equal to 4 in Z6. So therefore, 2 and 4 are associates. So apparently, there are cases where this theorem is still true outside the context of R being an integral domain. All right? Like Z6 is not an integral domain. It's got 0 divisors. 3 and 2, right? Now, if you're like, well, do you have an example where, it's not an integral domain and, you have non-associates generating the same, principal ideal? Well, I don't have an example, but there's a link in my notes to a Math Stack Exchange Q&A about this, so you can look there. It's probably not that easy if I had to do that when I wrote the notes. All right. Or maybe I'm just missing something obvious. All right, so that brings us to the first theorem for today. If I can find my pen. Here's the theorem. Theorem in a principal ideal domain, comma, x is prime. I probably shouldn't say x. Let's say a is prime. Yeah. If and only if a is irreducible. Right? Now, part of this has already been proved last class, right? Because right here, right, but PID is, among other things, this is an integral domain, right? Where what? Every ideal is what? Generated by what? One element. Not the same element, of course, but different ideals, different elements, but every ideal can be written as being generated by just one element. Every ideal is principal, right? It's just multiples of the ring.
Sorry.
Okay. Guys got a bad case of the giggles today. I blame Dr. Schweitzer. It all goes back to that. Let's see here. So, which direction do we already have? Up here. So this is an integral domain. So if it's prime, it's irreducible, right? So there you go. Half of our work is done for us last time. Done by theorem 4.7.8, right? So we need to go and investigate the other direction. All right? So let's suppose A is irreducible. All right? Our goal, our mission, should you choose to accept it, is to prove that A is a prime element. All right? And so we probably should remind ourselves what the definition is of prime, right? So what is it? We'd like to show, parenthetical comment up here, right? Where we wish to show A is prime. So how do you test that? Basically, the definition of prime sort of reverse engineers Euclid's lemma to be the definition. And so the situation is this: if A divides BC, that has to imply either A divides B or A divides C, then A is prime, right? So that's our definition of prime. So what we're going to do is suppose that B and C are in the PID, which I guess I'm going to call D here, with A dividing their product. All right? And then I'm going to let I equal to AX plus BY such that X and Y are in the domain. So I is an ideal, notice, is an ideal, right? You could prove that, right? I'm not going to stop and do that because it's routine at this point for us, but we can prove that's an ideal. Because the difference of such things is again such a thing, so it's a subring, and it's uber closed, right? So it's an ideal. And hence, there exists D in the domain such that D generates I. All right? But of course, A is equal to, well, A times 1 plus B times 0, is it not? And that's an element of I, which is, equal to the set generated by D, which of course implies that A is equal to, like, R times D for some ring element in the domain. So A has to be equal to R times D, but A is irreducible. So what do we get to say? Yeah, R or D is a unit. Is a unit. Don't worry, I didn't hear what you said.
Yeah.
Your secret's safe with me. Is a unit. All right. So case number 1. All right. If D is a unit, then what can we say? Yeah, I mean that's true. D is then D is equal to D. Thus, well, certainly we can say that C is equal to times AX plus BY, right? Like I can make this 1. I can choose X and Y to make that 1 because it's everything, right? So there have to exist particular ring linear combinations which attain the unity in the ring. And of course I can write C like that. And as such, what's that tell me? I'm like, okay, so I rewrite this as ACX plus BCY, right? We find that A divides ACX, and we were given that A divides BC, right? So if A divides this and A divides that, A divides C. Thus, A divides C. Number 2, if R is a unit, right? If R is a unit, then A is equal to RD implies that A and R are associates, right? Hence, the principal ideal generated by D is equal to the principal ideal generated by A is equal to I. Yeah, I think I do. Thank you. I definitely mean that. Although it is not what I wrote. Yeah, it's got to be D. Otherwise, this wouldn't follow either, which is what I need, right? Which, of course, then implies what? This implies that B, which, by the way, is equal to A times 0 plus B times 1, is an element of I, which implies that B is equal to A times lambda for some lambda in the domain, which implies that A divides B. All right? Therefore what? See what's happened in case 1? We have A divides C. In case 2, we have A divides B. So, thus, A is prime. And there you have it. Let's see here. So example, I don't know if I have it. Yeah. Example 2. The integers are a principal ideal domain. And we know what it looks like. The ideals are generated by n, right? That's what the ideals look like in the integers, of course. This is, famous example. And one of the interesting things to think about any ring is, does the property of the ring transfer over to the property of the polynomials over that ring? Sometimes it works, sometimes it doesn't. Here it doesn't, because it turns out that z polynomials with integer coefficients is actually not a PID. Why? Well, we just need to give an example of an ideal which is not principal, right? So the standard example which is given is this. Let I be the ideal generated by 2 and x. All right? So, like explicitly, what this thing looks like is 2 times, say, f of x plus x times g of x, such that f of x and g of x are polynomials with integer coefficients. So why is that not principal? How do you show something is not principal? Right? Probably it's a proof by contradiction. There are other things. We have a lot of theory in play. So we'll have other tools at our disposal as opposed to just, direct battle. But at the moment, direct battle is the way. So assume that there is, assume that I is equal to, the principal ideal generated by a particular integer polynomial d of x. Then that would imply that one thing, 2 is equal to, let's see here. I better follow my path. All right, so I was like, okay, so if it's generated by d, then x is in here, and 2 is in here, right? Which means that x can be written as a multiple of d of x times some g of x, right? And likewise, 2 can be written as a multiple of d of x times some, let's say, h of x. All right? And so, if you go back the other day, we were talking about, those polynomials 1 plus x and 1 minus x, and I mentioned you'd run into trouble showing that they were comaximal for zx, right? So the argument I'm about to give you, you could do something like I'm doing right now to prove what I asserted that other day. And basically, just evaluate. If we evaluate these equations, let's call them star and star star. And there's probably a bunch of ways to attain this contradiction, but here's the way I'm going to do it today. If I evaluate at 0, which is something we can do to polynomial equations, right? That gives me 0 is d of 0 times g of 0. And we also have 2 is equal to d of 0 times h of 0. So this right here implies that g of 0 has to be equal to 0. Because h of 0 equals to 0 is not an option, right? Since, d of 0 is not equal to 0 by star star, right? Well, let me say by this Pac-Man. All right? So g of 0 is 0. But what does that mean? That means that g of x has to have the form like c1x plus higher order terms, right? And so x is equal to d of x times c1x plus higher order terms, right? But what does this imply? If you have equality of x with d of x times c1x, what can d of x possibly be by the rules of polynomial algebra? I'll repeat that. This equation right here, if x is equal to some polynomial, we don't know, mystery polynomial, times c1x plus dot dot dot, because this is the form of g of x. See, g of 0 is the constant term. It's gone. It's gone. It's no more. What? Right, d of x has to be a constant, which says that x is equal to like d naught times that constant times x, right? But d of 0, let's see here. But we also know that 2 is equal to d sub 0 times h of 0. Right? Oh, but we know more than that. We know more than that, right? Actually, let's dwell on this. I mean, this is true, but not helpful, all right? So ignore that. Let's focus on this. What does this tell me? This tells me that d0 times c1 has to be 1. Right? Which tells me that I either have d0 equal to c1 equal to 1 or d0 equal to c1 equal to minus 1. Them's your choices. Either one of them is unacceptable, see, because plus or minus 1 generates the whole kit and caboodle of these, of the polynomial with integer coefficients. And that's a problem because definitely this ideal is not everything. Right? Look at this ideal. It only allows for even coefficient polynomials. But what if you have an odd constant coefficient polynomial? That's not attainable in this ideal. Therefore, this is a contradiction. Let's see here, like, 3, for example, 3 plus x is not an element of I. All right. So what does this all mean? So here's my question, follow-up question then, right? Is it possible for the ring of polynomials with integer coefficients, is it possible for it to be a words, PID? Well, I guess we just proved it's not a PID, right? Let me say it. That was not the question I wanted to ask you guys. Rats. All right, so the next theorem, we'll have to come back to my questions because let's see here. So example 3. Excuse me, not example 3, my bad. Proposition 1. What? Man, you guys are giggly today. Let's see here. You say you're sorry, but I don't believe it.
You're right.
Don't believe it for a second. Put your sorries in a sack. Let's see here. Proposition 1. Sorry, I'll behave. Proposition 1. Every ideal in a Euclidean domain is principal. In fact, if I is a non-zero ideal, then in a Euclidean domain, then I is generated by D, where D is any non-zero element of minimum norm. Minimal norm. All right. So the proof is really quite straightforward. What we do is we assume we have a Euclidean domain, all right, and with norm n, so let's let D be Euclidean domain with norm n and I not equal to 0 and ideal, then if you form S to be the set given by norms of X such that X is in the ideal, what can you tell me about this set? This is a subset of what? This is a subset of natural numbers with 0, right? In fact, this is a non-empty set of positive, well, non-negative integers, which is bounded below. Therefore, it has a what? Hence, by the well-ordering principle, by the WOP, the well-ordering principle, S has a smallest has a smallest member Emma. No, S not. Hence, there exists X naught in the ideal such that the norm of X naught is equal to S naught. All right? Period. To show, all right, so I'm trying to show that ideal, the one generated by X naught, actually is going to have everything in it, right? So like let let, I think Q, no, Z, my bad. Let Z, got my letters mixed up here, Z be an element of the ideal and apply division algorithm, right? Which we can because this is a Euclidean domain to select Q and R in D with what? 0 less than or equal to the norm of R less than the norm of X naught. And of course we've got Z is equal to QX naught plus R. All right. So that means then that we can solve for R. Well, first of all, let's take stock in where things are. Notice that Z is an element of I. That was by assumption, right? And so QX naught is also an element of I. Why? As X naught is an element of I, and so by uber closure we have QX naught as an I, right? So what that shows you though is that thus R is a difference, right? R is equal to Z minus QX naught, which is a difference. It's a difference of elements in the ideal, and as an ideal is a subring, consequently R is an element of what? It's an element of I. All right? But this forces, what is this force? This implies that R has to be equal to 0. Why is that? That's right. So it must be 0 because to say otherwise is to contradict the construction of X naught. It would give us an element of smaller norm than the smallest normed element. So we must have R equals to 0 by minimality of X naught. I'll just say by construction of X naught. And then what? Therefore, Z is equal to QX naught, which of course is an element of the ideal generated by X naught. So, which tells me, of course, that the ideal is a subset of the principal ideal generated by X naught, and it's also clear that X naught is a subset of I, because X naught, an element of I, implies the principal ideal generated. This is a general lemma. If you have an element of an ideal, the principal ideal of that element is a subset of the ideal which contains the element because of uber closure. Or not even that, just regular closure. So therefore, the ideal is equal to the ideal generated by X naught, and that's it. All right, now I can ask you the question, follow up to example 2. Example 3, Z of X is not a blank. There does not exist any blank on ZX with a blank blank. Blankety blank 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 blankety. Lots of blanks. So, look. So let's see here. It's not a Euclidean domain, right? Why? Because it's not. If it was a Euclidean domain, it has to be PID, but it's not, right? So it's not a Euclidean domain But I'm saying something very strong here. I'm saying there does not exist any norm on ZX with a division algorithm. So this forbids, in the infinity of possible norms you could build on this ring, you know that they're all doomed. None of them can possibly live up to the division algorithm. It can't happen, because if it did, that would make the integer polynomials a principal ideal domain, which it's not. We proved it. All right? So, let's see here. So I think it's important to see the things I just went through done slowly and methodically, and so I did, as well, maybe not, maybe that may be a slight overstatement of the slowness of my presentation. I mean, I was just covering retarded springs in the previous class, so I'm a little bit retarded at the moment, but let's see here. What's that?
What kind of springs?
Retarded springs. They're slow. Slowed by friction, that is. Let's see here. That's what I call them, yeah. I mean, it's in other textbooks.
Do they call that in textbooks?
Yeah.
Do they actually?
Yeah, it's in textbooks. It counts.
Ones that you wrote?
Ones that I wrote. Don't be, oh, wait, never mind. All right. So, listen, let's draw some ideas together. I've talked about some of these things before, but I should talk about them again. So, we have multiples, we have divides by, right? It's a multiple, means you can write one as a multiple of the other. Multiply of some ring element. B is a multiple of A. In that case, we say B divides A, right? We can talk about the greatest common divisor. This is the thing I want to talk more about. We'll just start talking about it today. I won't finish. But, you know, if D divides A and D divides B, that makes D a common divisor of A and B, right? And it's the greatest common divisor. If you have any other divisor, that divisor must divide the greatest common divisor, right? And so we have this notation, GCD of AB is equal to D, but we also, maybe you've seen this notation, A comma B for the GCD. This is another common notation. It's a good notation in the sense that it anticipates the way that ideal formulation works. In principle, the ideal generated by the GCD of A and B is the principal ideal containing A and B. That's how this all works, actually. So at the level of ideals, we have B divides A is equivalent, right, to, how's it go? Oopsies. Daniel has lulled me into a false sense of security. So B divides A means A is an element of the ideal generated by B because A is a multiple of B, right? But that means that the ideal generated by A is actually a subset that's contained in the ideal generated by B. So you notice that the flippity-flopping of the order of the letters here, we get containment in the sort of opposite order there, right? And so if D divides A and D divides B, that means that the ideal generated by D contains both the ideals generated by A and B, and in particular the ideal generated by A and B, like that. And then of course, if we have D prime divides D, that means that the ideal generated by the GCD must be a subset of the ideal generated by anything else. What did I do, Shane? You, nothing? Oh, okay. So it wasn't about what I was saying, it was, well, it's the back of Emma's head. It's just funny looking, I guess.
Hey.
But sorry, it was not really. It was really an unnecessary strike against Emma, but I'm sticking to it. Let's see here.
You can do my hair next.
I can do your hair next. I only do buzz cuts. So so proposition 2: if A and B are non-zero in a commutative ring, all right, then the ideal generated by A and B is in fact the principal ideal generated by the greatest common divisor of A and B. That's what this all means when we put it together, all right? And so I really think we should generally say that D is an element of the GCD because the greatest common divisor is not a single thing, it's a set of things more generally. It's just a quirk of integers that it's just one thing. Because even in integers, the GCD can always be plus or minus what you say. You say the GCD is 10, I say it's plus or minus 10. You say the GCD is 67, I say it's plus or minus 67, you know, just to pick out a random number. But you know 67 is prime. You know what 331 is? 300. The 67th prime, very good. What's 4489? What's 4489?
Oh, was that on a test?
67 squared. That's here. So, all right, I'll shut up. You know what 19 is?
19?
Yeah.
What?
It's the prime, which the 67 is. It's like it's the 19th prime. Let's see here. So these are stupid things I know. All right, so the brain rot will stop now. So R is a Euclidean domain, A and B non-zero elements in R. If D equals Rn is the last non-zero remainder for the Euclidean algorithm for A and B, then D is the GCD of AB, and the principal ideal generated by A and B is generated by that GCD. And I say that, but I should say a GCD because it's not unique. All right, could be there's many choices generally. And in particular, there exist x and y such that D is equal to AX plus BY. Number 3, D is unique up to multiplication by a unit though. At most, the different choices of GCD correspond to whatever informs what makes associates in the ring, right? So that's why I said plus or minus in integers because the only units in the integer ring are plus or minus 1. Now the proof is on page 275 of Dummett and Foote, and I don't really think it's worth our time. Because it really is just the proof of the regular Euclidean algorithm put into place here. Of course, now that I've said it's not worth our time, Violet will immediately go and look at it, perceiving that it must be important. See, I don't think Violet's ever watched Seinfeld, but there's this episode about like Bizarro Jerry and it's relevant. Anyway, proposition 7. Every non-zero prime ideal in a principal ideal domain is in fact a maximal ideal. And I feel like we might have proved this one actually the other day. We proved that prime implies maximal. Remember that? We did that a few classes ago actually. It is on page 280 of Dummett and Foote if you want to see a proof there. Corollary, if R is any commutative ring, such that the polynomial ring is a PID, then R is necessarily a field. All right? Here's how the proof of that goes. If R is a PID, R of X is PID, then since R is a subring, it must be that R is an integral domain. And so then if we look at R of X mod the principal ideal generated by X, well, we can see that this must be a prime ideal because the quotient of R of X by the ideal generated by X is just R again. But R is an integral domain, which makes this a prime ideal because the polynomial quotient ring is a integral domain. But we're in a PID, right? So if it's prime, it's maximal. Therefore, this is also a field. Because, you know, if the quotient ring, if you're quotienting an integral domain by a maximal ideal, we have a field, right? We proved this before. All right. So these examples are important, and there's a calculation in here. There's actually something genuinely new I want to show you for a second here. This is just a rehash of what we already did. 2 with X, non-principal ideal. All right, so since we have a since 2X is a principal, wait a minute. Oh, I'm sorry, I can't read my own example. But this, on the other hand, is a principal ideal within the polynomials over a field that contain 2. Why? Because polynomials over a field are in fact the Euclidean domain like we talked about last time with respect to the norm given by the degree function. We'll talk more about that in future lectures. So therefore, since this is a Euclidean domain, that implies that it's a PID, because every Euclidean domain is a principal ideal domain. All right. This right here is a cautionary tale. Here we have z adjoined the square root of minus 3. In this, there's a norm. The norm is given by a squared plus 3b squared. Just because there's a norm doesn't mean it's a Euclidean domain. Remember, there has to be a Euclidean algorithm. A norm alone is not sufficient. Now, this norm has super nice properties, like the norm of the product is a product of the norms, like that. And also, the other thing here is the norm of 1 is 1. So that means the only way you can have a unit in z adjoining the square root of minus 3 is to have a squared plus 3b squared equals to 1. What are the solutions to that using integers? Tell me. I have a squared plus 3b squared equals to 1. What are the solutions?
1, 0.
Yeah, just 1 and 0, right? Plus or minus 1 and 0. So the units in z adjoining the square root of minus 3 are just 1 and minus 1. In contrast, we looked at the Gaussian integers, and we'll look at them again here in a minute. There, you have a squared plus b squared equals to 1. So there are 4 solutions. There are 4 units in the Gaussian integers. If you do z adjoin the square root of minus 1, you actually have 4 units. And that means when you look at GCDs in the Gaussian integers, you have 4 choices. Here, you just have 2, just like regular integers, if there was such a thing as a GCD. I don't think there is, but because I don't believe this is a Euclidean domain for reasons I'm about to show you. So suppose you have 1 plus root 3 is equal to xy. Right? Then, if that's the case, then 4 is norm of x times norm of y. The only way that can happen for one of them, for both of them not to be units, is they must both be 2. I'm trying to show you that it's irreducible, right? So if it's irreducible, that means any factorization must have a unit. See, that has to happen because if I did have 2 and 2 here, that's the only thing I can do. It's also unattainable because there is no solution to this. You try it out. Plug in a and b integers. You can't solve that. All right? You can't solve it. So therefore, x or y must be a unit, which shows you that any possible factorization of 1 plus root minus 3 is necessarily a reduction into a unit times an associate, basically. Anyway, so long story short, irreducible. But we can also prove it's not prime. So this is an irreducible, which is not prime. So check this out. We have 1 plus root 3 minus 3, 1 minus root 3, like this. The product of this and that gives me 4, which is 2 times 2. So that means that this 1 plus root minus 3, it divides 4. It divides 2 times 2. And yet we can prove that this does not divide 2, and this does not divide 2. Okay, so it doesn't divide the b or the c, therefore it's not prime. How do we do that? Well, if we did have this times this equals to that, that would give me this equation, which gives me these 2 equations, which gives me these 2 equations, which tells me a has to be a half, which is generally frowned upon for integers. Right? Yeah. Therefore, 1 plus minus root 3 is not prime. Therefore, z adjoining the square root of minus 3 is not a PID, because we just proved in a principal ideal domain, what? What did we prove? In a PID, A is prime if and only if A is irreducible. So in this ring, we have an irreducible, which is not a prime. Therefore, it is not a PID. Therefore, it is not a Euclidean domain either, because every Euclidean domain is automatically a PID. There's also something really weird happening here. We have a way of factoring 4 in this way and also in that way. Something funny is happening with factoring here, because you can prove that those different factorizations of 4, it's not like we're just taking a unit and reordering the factors, right? Like these are not associates. 2 is not an associate of this or that. The only associates, the only units you have to work with here are 1 and minus 1. There is no way. Those are 2 inequivalent factorizations of 4. right? There's something else there to think about, factoring. So another example, which is given in Dumb and Foot, which I'm not going to get into, but z adjoin 1 plus root 9 minus 19 over 2 is an example of something which is actually a PID, which is not a Euclidean domain. The proof of that is somewhat involved, and I'm not going to, like, I just want you to know that that's an example. I'm not going to hold you to the details there. He has this whole discussion of side divisors and things. I'm not covering that, okay? So relax. Unless I assigned a homework problem, in which case I retract nothing. But I don't think I did. I don't think I did. Here's another example that's much like the one I already showed you. If we look at z adjoin the square root of minus 5, 3 is irreducible, but it's not prime. I just want you to like feel that for a second. 3 is not prime in z adjoin the square root of minus 5. That's a little weird, but it's true. And the if we look at 2 plus minus root 5, 2 minus root 5, it's equal to 3 squared, all right? But, so this is divisible by 3, yet 3 does not divide this or that. Consequently, 3 is not prime. And again, this is not a PID. So ultimately, we really want to understand the following storyline. Fields, there's fields, then there's Euclidean domains, there's PIDs, there's UFDs, and there's integral domains. Each one of these being properly contained in the other one. So the polynomials with integer coefficients are a UFD, which is not a PID. I've explained that today in some detail, right? This right here is a integral domain. Yes, that's true. But it is not a unique factorization domain. That's what UFD is. Unique factorization domain. I haven't quite fleshed that out yet, but you can see it in the, well, if we go back to z adjoin the square root of minus 3, we can put that here too. It's more clear there because we saw that 4 can be factored in 2 different inequivalent ways. So it's not a unique factorization domain. There are elements which have dissimilar factorizations, which are not, you can't get from one to the other just by associating, all right? By association of elements. PID, which is not a Euclidean domain, would be that thing I told you about with the side divisors. What's a Euclidean domain that's not a PID? Oh no, every Euclidean domain is automatically a PID. Right. But yeah. So I actually have an example of the Gaussian integers I wanted to show you guys. So Gaussian integers are z adjoin, I, right? So a plus bi, like that, all right? And so the way to do basically the way to do the division algorithm, they're complex numbers. So essentially you just divide the complex numbers and look for like the closest multiple that's relevant to your problem. Let me actually show you specifically. So, that is whatever it means. I think it's maybe better just to look at the example explicitly here. Yes, discussing class. Here we go. So I have A is 11 plus 3i, and that's my A plus IB. And I have beta is 3i plus 2, which is my C plus ID. In the notation, I had A, B, C, D, and then in the proof above. So I'm doing A plus IB divided by C plus ID, all right? And so what I did was I actually just, divided this by that. They're complex numbers, so you can divide them. And I figured out that gives me a, so this is the first, oh, by the way, this is the vector Euclidean algorithm. So the vector Euclidean algorithm you might not know about, but you should. What you do is you don't just you write A comma B is equal to the A and the B, whatever the numbers are. And then you just keep the A and B symbolically all the way on down, and it will automatically derive for you the Bazoo coefficients that you need to form the GCD. This is the vector Euclidean algorithm. I learned it from Dr. Smith, who was here, and he's an honest-to-goodness number theorist. It offends him that it's not taught. Anyway, so I start out, it just sets the notation. This is alpha, this is beta, right? Next up, I can pull out apparently, so the remainder, the original dividing number goes here. This is the first remainder, 1 plus I, because apparently, if you do alpha minus 2i times beta, that gives you a remainder of 1 plus I. I used a calculator, all right? Probably Wolfram alpha. And then, notice that this simplifies to, well, anyway, this 1 plus I comes down here, and then I'm left with the remainder of minus I from doing this stuff right here, right? At this point, I'm done, because that's a unit. I mean, I know that the next thing's going to be 0. Then at the last non-zero remainder, that's like getting a plus or minus 1 in the regular Euclidean algorithm. And so, because of all this, I can see that minus I is equal to this stuff. So there you go. And you can reformulate this, and you can see, in particular, the, Gaussian integer linear combination of alpha and beta, which forms minus I. Namely, 9 minus 4i times beta minus 3 plus I times alpha gives me minus I. And of course, you can reformulate this to give you back 1. You want to get 1, we'll just multiply this by I, and out pops that. So the greatest common divisor of 11 plus 3i and 3i plus 2 is 1. Or, as I say here, you could say minus 1i or minus I. So that means that this ideal and that ideal are what we say comaximal. They're comaximal ideals in the ring, in the Gaussian integers, and they give you the sum of them being the whole ring. I wanted to show you that example. It would take me a half hour to work out the numerics in class, right? But it's straightforward what to do, actually. You just divide numbers like complex numbers, and just basically pick the, when you sort through it, it's actually not that complicated. It's unfamiliar. Now, all of this leads us to the study of, well, these z adjoin square root of minus d, or square root of d, where d is square free. These kinds of things were known to mathematicians in the mid, let's say, 18th century, like Euler and Lagrange worked with these kinds of things, right? And there's like a whole beautiful algebra of how to solve something called Pell's equation using these. Like if you have one equation, there's a group structure, and you can create more solutions from that one solution using this. Basically, these particular rings encode solutions to very particular Diophantine problems. Here's a stupid example of this kind of thing. If I have 3 squared plus 4 squared equals to 5 squared, right? I could multiply that by 2 and get a new Pythagorean triple. You ever notice this? Maybe 4 is better. 6 and, what did I just say, 3, 4. So 6, 8, 5 times 2, 10. Right, you can generate all kinds of new Pythagorean triples from a given triple. It's that kind of thing, but in the more abstract. And so, like this problem, finding integer solutions to that is Fermat's last theorem, right? That doesn't have interesting solutions for like n greater than or equal to 3, I think, right? Isn't this Fermat's last theorem? I'm not remembering it exactly correct, but anyway, proofs of this theorem can be constructed using these rings that we're seeing, and one of those proofs assumed unique factorization. And it was a wrong proof because of that. And so that's what I'll try to talk more about that next class, but that's where we got to today, so I'm relatively. So like the end of this lecture, we didn't actually get to, I'll recycle it for the next one, so sorry guys.